Hi, my name is Lloyd Lobo, and I will be discussing spectral domain optical coherence tomography via Acousto-Optics. Let me begin by discussing how the Michelson interferometer laid the foundation upon which OCT is built. A simple schematic is shown alongside. You have a source that sends light, splits it by the beam splitter, is reflected back via mirrors, and is detected using a detector. So the light travels different path lengths, XR and XS, and this corresponds to a phase difference in the interference signal. This phase difference creates interference fringe patterns, which are detected using the detector, and these signals can be analyzed to provide information about material properties on the sample, on what we call the sample arm. So moving on to SD-OCT. OCT uses a broadband source with multiple wavelengths. These wavelengths are focused using a lens like here and focused onto a point on the sample. Different wavelengths reflect at different depths in the sample, are sent back to the beam splitter, interfered with each other with the reference arm, and via a diffraction grating in the spectrometer are separated and then detected. Now this provides the depth information of a single point on the sample, and the sample can be scanned in 3D, scanned in 2D laterally to provide a 3D scan. Here we can see the signal that we detect for each wavelength, and it depends on the path length difference between the sample and reference arm. This provides us with an image, and I will be now going over the advantages of using Acousto-Optics with this system. So the drawback of using only a lens is that we have lower signal as we go deeper into the sample. So what if we use an active focusing element like a transducer? A transducer can create a standing wave which changes the medium pressure, thereby changing the refractive index of a medium, and focusing light using this concept of how an optical fiber works via critical angle reflection called total internal reflection. Light can be focused at a plane depending on the intensity of this ultrasound, and the frequency and phase of the ultrasound peak cycle has to be matched with the light source. So this provides us with an opportunity to actively change the area where the sample is being where light is being focused on the sample. And in addition to this, a lens has a Gaussian depth focus, whereas this transducer has a Bessel-like focus, achieving a higher depth of focus. So what are the features? As I discussed, it's that ultrasound transducer can have a Bessel beam focus, and it provides tunability by changing the amplitude of the transducer. We can change the focal plane, and turns out we can get pretty good OCT signals back. So here I have a scan of a 2D mouse paw, and you can see some of the bone structure in here that's reflecting pretty well as opposed to letting it through or getting scattered along the skin of the mouse paw. So this gives us a pretty good understanding that OCT using Acousto-Optics can be used to image biological samples. The problem with OCT using Acousto-Optics is that transducers have thermal drift, and that could cause PSF inconsistencies. And syncing of the ultrasound peak with the light source reduces the input signal, as we only turn on the laser for a shorter duration as opposed to continuous wave modes. So what can we do in the future? We can combine lens-based and cascade systems via joint bilateral filtering, make use of the depth benefit of the cascade system with the lateral benefit of a lens-based system. use traveling wave transducers to use ultrasound in media instead of externally, and leverage refocusing of slightly scattered photons caused by transducers. So this proves to be a viable method to implement OCT, and we hope to see more of it in the future. Thank you.